Hi everyone, I am S Kiran. I would like to discuss about junction diode characteristics. Subject name is electronic devices and circuits. Okay, previous video I have discussed about theory of PN junction diode and energy band diagram of PN junction diode, open circuited PN junction diode, biased PN junction diode. Now in this video I will discuss about current components in PN junction diode, diode current equation and VA characteristics of PN junction diode. Okay, now before going to the current components in PN junction diode, what are the majority charge carriers in P type and N type? The majority charge carriers in P type holes. Okay, the majority charge carriers in N type electrons. Based on these charge carriers, it constitutes some current. One is electron current and second one is the hole current. Okay, this is some introduction about this current components. Now previous lecture, just have to show some quick reference. See here, some energy band structure and theory of PN junction diode. See some diagrams and V0 built-in potential or a potential barrier, width of the depletion region W, right? Energy band diagram, open circuited step grade PN junction. Okay, biasing of PN junction diodes, two conditions, forward bias and second one is reverse bias. Okay, now now we will enter into the current components. Okay, see here, current components in a PN diode. See here, this is a structural diagram. So here we can expect two type of currents. One is hole current and second one is electron current. You know, in P type the majority charge carriers are holes. That's why we get some large current here, a little bit reverse saturation current, that is called INP. This is IPP, this is a hole current in P side. INP, electron current in P side. Okay, this is two currents. Coming to N type, see here, in N type there is an N type, there is electron current. Okay, electron current, that is called INN in N side. IPN, hole current in the N side, right? These are the current components of given PN junction diode. See here, what is high? Okay, I is nothing but IPN plus INP. Okay, IPN plus INP. This is the total current. Okay, this is one of the current component of PN junction diode. Just read the theory, you can understand what are the different types of current components in the PN diode. Okay, IPN comma INP. IPN is nothing but what? IPN we can call it as a whole current. Okay, what about INP? This is the electron current in the P side, right? These are the current components equations. IPP of n is equal to I minus INP of n. Just you can write these equations, this is more than enough. Okay, these are the different current components in the PN junction diode. First, simply you can draw this diagram. This is important diagram to identify these currents: hole current, electron current in P side, electron current, hole current in N side. Okay, these are the current components in a PN junction diode, right? Now we will concentrate on diode current equation. Okay, you have write diode current equation in this diagram also. So see here, how to derive, nothing to worry about derivation, just simply you can concentrate how it can be used, how it will come, this current equation. See here, based on the diode characteristics, see here, there is a variation like exponentially. It is a non-linear device, absolutely. How it will be variable? That this to draw characteristics, to draw graph between voltage and current, we can expect the graph exponentially, right? We can expect graph some exponentially. There's something e to the power of something. Okay, if you want to the current is in terms of e to the power of something. Okay, if you can observe the graph, there is exponentially change with respect voltage to current. Okay, based on these characteristics, we can define one current equation, that is nothing but the diode current equation. Okay, what diode current equation said relating to the voltage and current? So there is a relationship between voltage to current is nothing but the diode current equation. See here, I will show one diagram like this exponential. This is voltage and this is the current. So what happened? I is equal to some e to the power of v. So there is a exponential increase here. Okay, right. See here. Now we can read how it will get. So diode current equation relating the voltage and current is given. So this is the diode current equation. So read here, very important. We can do so many problems by using this diode current equation. What is diode current equation? I is equal to I naught into e to the power of v by eta vt minus 1. This is the diode current equation, which is the relation between current and voltage. Okay, which is the relation between current and voltage. Right, this is the diode current equation. Right, see here. Now what is I here? I is nothing but diode current. See, one by one I will read carefully, very important. I is diode current. Then what about I naught? I naught is equal to reverse saturation current. Reverse saturation current. V is external voltage applied to the diode. Eta a constant. Eta is a constant. 1 for germanium, 2 for silicon. So what about Vt? This is Kt by Q. So Kt by Q means this is volt equivalent of temperature. So Vt can be called as a volt equivalent of temperature, that is thermal voltage. So sometimes there is asked to chance in our Viva examination. Okay, at the time of Viva, what is Vt? Vt is called thermal voltage or volt equivalent of temperature. Underline, very important, volt equivalent temperature or thermal voltage. That is Vt is equal to Kt by Q. It's also T by some 11,600. Right, see here. Now what about K? K stands for Boltzmann constants, 1.3 into 10 to the power of minus 23 joule per Kelvin. What about Q? Q is nothing but charge of the electron, 1.6 into 10 to the power of minus 19 coulombs. What about T here? T is the temperature of the diode. See, one by one I will read one by one here. Diode current, diode reverse saturation current, external voltage, eta, Vt, K, Q and T. Right. Now once again I will read diode current equation. I is equal to I naught into e to the power of V by eta Vt minus 1. Vt means volt equivalent of temperature. Right. Now for example, if T is equal to 300 degrees Kelvin, nothing but room temperature, how diode current equation is converts? See here, this is the diode current convert equation, converts into like this. That is called I is equal to I naught into e to the power of 40 into V by eta. For example, here some were exceptions. If separately, if germanium having eta equal to 1, silicon eta value equal to 2, substitute these two values also here and neglect this 1. So how we can write this expression? Okay, see here, for germanium, the diode current equation I is equal to I naught into e to the power of 40V. For silicon, I is equal to I naught into e to the power of 20V. A simple expressions we can directly use in the numericals or problems. Okay, see here one more problem. You can understand the total concept. When a reverse bias is applied to the germanium PN junction diode, the reverse saturation current at room temperature 0.3 microamperes. Determine the current flowing in the diode when 0.15 volts forward bias is applied at room temperature. See here, what is the question? Simply asks what is the diode current equation. What is diode current equation? I is equal to I naught into e to the power of 40 Vf minus 1. So why here I write 40 Vf? Because it is a silicon diode. Here mentioned, sorry, it is a germanium diode. See here, it is a germanium diode. That's why we can write here e to the power of 40 Vf minus 1. See here, all data is given in the problem. What are the data? I naught is given, that is 0.3 microamperes. Vf also given, that is 0.15. Simply substitute these values in diode current equation. We get the current. That is called the flowing through PN junction diode under the forward bias. Okay, reverse saturation current I naught is given. Okay, across the diode 0.15 also given, that is germanium diode. That's why we can write 40 Vf and the exponential side. Okay, that finally we get 120.73 microamperes. Okay, right, this is the problem, okay, of diode current equation based on the diode current equation. Now this is theory. Now we will concentrate on volt-ampere characteristics. So see here, again I will concentrate on biasing concept. See here, what happened in the forward bias? See, in the forward bias, the majority charge carriers in p type is the holes, in n type electrons. What happened? These holes are always trying to repulse this positive terminal. See here, holes always trying to repel this positive terminal. What about electrons here? Electrons is also trying to repel this negative terminal. So what happened at one time? See here, already I discussed in the previous lecture. I think you get more knowledge about the topic. Again I will discuss here because of this VI characteristics of diode under forward bias condition, or volt-ampere characteristics. We can also call volt-ampere characteristics. Okay, as shown in following figure, battery acts opposition to the internal potential barrier. Now what happened? Due to ripples, the charge carriers are trying to move cross over this junction. So what happened here? See, I will explain. For example, take here, there is a V and I. Okay. For example, if you apply voltage across the diode 0 volts, generally we get 0 current in the milliamps, right? So what about if you increase the 0.1? Okay, what happened? 0 milliamps. 0.2, 0 milliamps. What about 0.25? What about 0.25? We can expect such a that is called 2 milliamps. So if it is 0.3, we get some large current, that is called 0.15 milliamps. See here, if it is germanium diode, we get these characteristics. See here, at 0 volts, see here, at 0 volts, 0 current, 0.1, 0.1 volts, 0 current, 0.2 volts, some 0 current. At current conduction starts at 0.25. So you can take one cut-in voltage, that is equal to 0.3 volts. Okay, for germanium, right? Now, so this is the characteristics for what? This is characteristics for germanium PN junction diode. Okay, what happened? How it will starts the conduction? Because of applying forward bias. Okay, due to forward bias, the current conduction is only one direction. The direction is in the only forward bias. Up to 0.3 volts, it still wait without without crossover the junction. Once it starts the crossover the junction, we can expect the current. So based on these characteristics, we can explain it clearly. Okay, for this is the germanium silicon diode. Let us start with silicon diode. See here, again I will tell you the characteristics. Just you have to tabulate the some formula. See here, this is this side V. Okay, this side I. Now 0 volts, 0 current, 0.2 volts, 0 current, 0.4 volts, 0 current, right? 0.6 volts. We can expect such current, that is around 2 milliamps, right? Now coming to 0.7, again large current around 15 milliamps. So based on these values, based on this calculation, we can draw this graph, right? This is nothing but volt ampere. Volt means V, I means ampere. This is nothing but volt ampere characteristics under forward bias condition. Okay, generally in forward bias we can expect milliamperes current. So in forward bias, diode is in on state. Okay, see this characteristics. Okay, now what about reverse bias? Reverse bias, there is no conduction. Why there is no conduction? Because of there is no further movement of charge carriers cross over the junction. If when current conduction starts, uh, charge carriers are trying to cross over the junction. At that time only we can expect the current. See here, if charge carriers are trying to cross over the junction, we can expect the current. Yes, in this condition, charge carriers are not trying to cross over this junction. That's why there is no conduction. In reverse bias, we get zero current. Okay, sometimes there is a chance to get due to minority charge carriers, we can expect some microamperes current. Okay, see here, due to minority charge carriers only we can expect some microamperes current in reverse bias. This is the VA characteristics under reverse bias, volt ampere characteristics in reverse bias. Okay, what about in PN junction diode? In PN junction diode, if we connected to the forward bias, we can expect some milliamperes current. If you connect in reverse bias condition, we can expect some microamperes current. Okay, this is very important concept of VA characteristics or volt ampere characteristics in general PN junction diode. See here, very important, a very small current in order to the few microamperes. Okay, few microamperes like this, few microamperes. For what? Reverse bias. Okay, what about forward bias? Forward bias is nothing but microamperes, right? Now our concept is volt ampere characteristics in forward bias and reverse bias. This is our topic, actual topic. So see here, you can understand how I can draw these graphs. Okay, this is for forward bias, this is for forward bias, this is for reverse bias. See one more point, in forward bias the diode conduction is starts due to it is in the on state. In reverse bias, the diode does not conduct, that is the diode is in the off state. That's why what definition said? Definition said that diode is a two terminal semiconductor device, namely it's having two terminals, one is anode and second one is cathode. The flow of current allowing in only one direction does not supports the other direction, so due to this condition, diode sometimes can be act as a switch. Okay, due to this condition, diode can be act as a rectifier. Okay, why it rectified? It's only conducts one direction, does not conduct the other direction. Now, application of the diodes can be used as a rectifier. It is used in the power supply circuits. It can be used as a clipper circuit. It can be used as a clamper. It can be used in the clampers, clippers circuits. Okay, this is the VA characteristics of PN junction diode. The final point of this characteristics, microamperes current expect in reverse bias, milliamperes current expect in the forward bias. In forward bias, diode is in on condition. In reverse bias, diode is in the off condition. Okay, at some stage in reverse bias, we can expect some reverse saturation current, that is called I naught. Okay, in further increasing of the reverse bias, we may get also some breakdown. Okay, that is nothing but the diode breakdown. At the critical voltage, a large reverse current flow and diode is said to be a breakdown region. Okay, in Zener diode, we can concentrate these breakdowns also. Okay, at what time we can expect breakdown region? At this critical voltage, a large reverse current flow, and the diode is said to be a breakdown region. Okay, I hope you can understand these current components and diode current equation and volt-ampere characteristics. Okay, next lecture I will discuss remaining topics. One more important point, in my description I have provided previous video link and these topics notes. Okay, please go through it, and if you have any doubts, please ask in comment section. Definitely I will clarify all your doubts. Thank you so much. Thank you.